Hi, my name's Mike Sklash. I'm senior hydrogeologist at the Dragon Corporation. We're an environmental consulting firm with offices in the United States and Canada. Today I'm going to do a very brief introductions to geology and groundwater. Now I want to warn you, this webinar may go a bit longer than the others that we've done in the past because it covers a lot. You may want to view the geology and the groundwater basics separately if your time is limited today. So I'm going to start looking at this case study that we've been doing for a number of years. It's the former Schilling Air Force Base in Kansas, Salina, Kansas, and it's one of our sites where it's a good example of why you need to understand the geology and groundwater in order to protect human health and the environment. During the Cold War in the 1960s, the Schilling Air Force Base was a strategic air command base that was used as a base for bomber missions to Europe. It was at this location where hundreds of drums of trichloroethylene were used every month to clean oil from the bombers on their return to the base. TCE was allowed to seep into the groundwater and the ground. TCE is considered carcinogenic. It's in the soil and groundwater where people work and live, and is heading toward the Salina well fields. We need to find out where the TCE is now, where it's going, how fast it's moving, and how to clean it up. To do this, we need to know the geology and the groundwater conditions. So at the Salina Air Force Base, we use 218 to 254 drums of TCE per month. This was a lot more than other bases, much more than other bases. So what? Well, the groundwater is moving to the city water supply, and people live and work above where the groundwater is impacted by TCE. So where are the chemicals now? What directions are the chemicals moving? How fast are they moving? And how do we clean it up? So we're going to look today at groundwater and how it moves and why geology is important in groundwater flow. We're going to talk about geology first, focusing on the very basics for both. So we broadly can classify geologic materials into rock and soil, or sometimes we call soil overburden. Rock is consolidated material. That means that it will hold up and not fall apart if you put a piece in your hand, for example. Whereas soil is unconsolidated, meaning it will fall apart if it's dry in your hand. So rocks are consolidated aggregate of minerals, and a mineral is a naturally occurring solid inorganic crystalline material with unique chemical composition. And in this slide we can see the I've got a close-up over on the right. This is a mineral, dark mineral that you're seeing, and you can see the interrelationship of the various crystalline minerals, that there's no space between the minerals. This is common in many rocks, and it affects whether groundwater can be present and moving. So there are three types of common rocks based on how they are formed. The first one is the most recognizable of the igneous rocks, what we're seeing here. Igneous rocks are formed from molten material. And the picture on the left is a landscape from Iceland. The rock on the left side of the photo on the right, the dark rock with, you can't see individual grains in it, is an igneous rock from a volcano. The rock on the right photo, you see individual grains of minerals. This is formed deep in the earth. It's also an igneous rock. The common elements from a groundwater perspective is the grains are interlocking. There's virtually no space for groundwater to be and groundwater to move. But we should point out in some volcanic landscapes like Iceland or Hawaii, there's larger scale volcanic features that can support groundwater flow. The next type of rock by method of formation is sedimentary rock. Sedimentary rocks are formed from particles or solution from pre-existing rocks. The picture on the right is from the Grand Canyon in Arizona, and this depicts typical things we see in sedimentary rocks. They're laid down in layers. They're typically light in color. Sedimentary rocks can form either from particles where there's space in between, and on the left side we see sandstone made up of quartz particles coming from pre-existing rocks. And on the bottom we see limestone. You can see shell pieces that come from pre-existing materials. The third type of rock, by the way it's formed, is called metamorphic rock. These are rocks that are formed from pre-existing rocks and changed or metamorphosed due to heat and or pressure. They're generally formed deep within the earth. And as a result, we see things like rocks being pulled apart by the stresses in the earth as they're heated up. And on the right, we see that there's very little space. The grains are interlocking, and that precludes a lot of groundwater flow. So what are some of the factors that affect fluid transport in rocks? And as we mentioned, the grains are interlocking generally, and as a result, they're not capable of transmitting groundwater from many types of rocks. But secondary features can form, like we see in this road cut, where there is a fracture or a break in the rock through which water is seeping, the dark areas that you see. And that's one of the ways in which rocks can transmit water. So the two main factors that control fluid transport of groundwater in rocks is porosity and permeability. Porosity is the ability to store water, meaning void spaces, like we can see void spaces in this rock on the left. And permeability refers to the ability to move water, and that relates to whether the pore spaces are interconnected or not. Another term for permeability that you may see is hydraulic conductivity. In general, rocks have little to no porosity and very low permeability as they're originally formed. But if they are affected by post-formation conditions, they may be able to transmit water. And here we see some examples of processes that can change the ability for rock to transmit water. This is called a talus slope here. This is rock has been falling off this face of limestone mountains in the Rocky Mountain area of Canada. On the lower one, we see rocks that are affected by weathering, by really abrasion in the Peru high desert. And on the right, we see a core of limestone that has been dissolved in certain areas, and that has affected its ability to transmit water. Structure also affects fluid transport in rocks, and it can be a very major factor. Fractures are simply breaks in rock that have occurred due to stresses or cooling But there are a number of characteristics of the fractures which will control the ability to transmit fluids. How frequent are they? How many fractures? What's the orientation of the rock? Because that will affect the way groundwater may move. What's the length and depth of the fractures? What's the width of the fractures, the aperture? And are the fractures infilled? Look, now we're going to look at some factors that affect fluid transport in soils. Soil is the main property that controls water movement in most soils. Is the grain size distribution, meaning the proportion of sand, silt, and clay sized particles. The more fine particles like clay you have, the less likely the soil can transmit water. And then there are some other factors. How did the soil form? How thick are the deposits? And are the deposits structured? And that means, do they have features that occurred after the soils were formed? So how can soil be formed? Well, here are some of the major methods from glaciers. Fluvial means they're river deposits, that like we see in this photo. Lacustrine are lake deposits. Marine are sea deposits, and residual soils are those that are weathered in place, so they're not moved at all, where these other ones are moved from where the rock originally was. Fluvial soils can be very complicated, and this is a site that we've been working on, when I mentioned in Kansas, and it's complex because of what we call meander deposits. And meanders are features that we can see on this slide that have rivers moving back and forth in these large loops that cross a river valley. And meanders have very distinct characteristics in different spots. So this is an area where this is kind of the inside of a meander loop, and that's where things like sand would be deposited. And the blue arrow is where it's the outside of a meander loop, where materials would be eroded. The white arrow indicates a meander, it's called a neck, where that could be cut off in a storm and basically isolate that meander loop. And the black arrow shows an old meander loop that has been cut off. And the reason that that's important is that the water doesn't move very readily in these cut off meander loops. And you would get clayey type deposits there. So because of these different parts of the meander loops in 2 dimensions, you get various types of material being deposited in various areas. But the meander model on the right, and I apologize because I can't find the source of where I got this picture, is showing the meanders in 3 dimensions. The yellowish colors are the most recent ones on top. We're looking from above, and the dark colored ones are the older ones. So they formed at an earlier time, and they've been covered by later deposits. Well, the thing here is that you could be looking in the recent deposits at a place where sand is deposited, but below that, it will be an area that there might not be sand. So in 3 dimensions, they're extremely complex.
Some discussion about brownfield monies.
Glacial deposits are deposits that are laid down either by alpine glaciers like we see here, or by continental glaciers that now exist in the northern Arctic and in the Antarctic. These deposits can be either directly laid down by the glacier or laid down by water associated with the glacier, and they can be very complex. This is a core from Michigan where we're looking at glacial deposits, and you can see the yellow arrow is pointing to an area of sand, and the arrow below it is pointing to an area of clay. So this is all in a vertical profile, and then the white is showing gravel. So you can have a lot of complexity in geologic materials, and the yellow white, the gravel would transmit water fairly well, but the intervening layer would not because it's mostly clay. Another thing you can get from glacial deposits are varve clays, and this is varve clay that we see on the left. And varves are kind of rhythmic deposits that you get in glacial lakes with the finer materials deposited during cold episodes, and the coarser materials being deposited during high flow episodes. But what you see in a vertical direction is a lot of variability. You can also have fractures in soils. These are fractured clays in Ohio, and you can see on this slide that most of the soil is clay and doesn't transmit water, but we can see these wet areas where the clay is fractured, and these fractures are vertical, so they're difficult to locate or identify when you're working in a fractured clay area, because they become less frequent with depth. They become narrower with depth. The aperture closes up, and they're vertical. So if we're drilling vertically, it makes it problematic. So how do you think that you could identify these if you're in an area where these are common? And it makes the ability to transmit water significantly different. So there's the massive and the fractures. So the bottom line is there's all sorts of different geological conditions, and these affect groundwater flow. So you need to understand the basics of the geology in order to know whether you're going to have a lot of groundwater flow or not, and what the controls on the groundwater flow are. So we're going to move into the groundwater portion of this webinar. And the question is, what is groundwater? Well, groundwater is all water below the Earth's surface. So no matter where you are, if you dig a hole deep enough, you're going to run into groundwater, unless you're in very, very, very dry areas or kind of unfractured rock. But you'll find groundwater. Sometimes it can be very close to the surface. Sometimes it can be hundreds of feet below the surface. So this is a conceptualization of how groundwater looks. Soil and bedrock can be thought of as a porous medium consisting of solids, which are the golf balls in the glass, and void space, which are the spaces between the particles. So that would be kind of the matrix in which the groundwater would exist. And then you just add water and you've got groundwater in a porous medium. This is kind of what you see on the right with, this is actually T, if you were wondering, filling up the pore space, but not the solid space. So the water table is a term we use, is the level to which the water fills the pore space in general. And we can see that in a hole that we've dug here. So that's the top of the what we call the saturated zone. So if we look on this little cartoon with the circles representing the solids, all the void space between the solids is filled with water in the saturated zone. But above the water table, if you were to look at that at what's called the unsaturated zone, and parts of the pore space between the solids is not filled with water. And that's generally what we see above and below the water table. So we're looking at this hole. One of the questions you may have is how quickly does water enter a hole? And this is a graph from some wells that we were looking at a site where we've drilled a hole, and these graphs are showing how the water level rose with time. And you can see some of these took 2 months to rise to a level. Others were right there. And the rate at which the water fills the hole depends on the geology. If you've got things like clayey soils, very fine grain, the water takes a long time to enter the hole or the well. And if you've got sand, it can come up right away. So groundwater is part of a continuum that we call the hydrologic cycle, which is the cycle of water coming from precipitation. It falls on the ground. Some of it runs off as overland flow. Other infiltrates into the ground. 4 is groundwater recharge, meaning the water actually reaches the water table. 5 is through flow. That's water moving above the water table in the unsaturated zone. 6 is groundwater discharge, where the water comes out into the surface water body. And 7 is evapotranspiration. That means the water given off by plants. And 8 is stream flow or lakes. So groundwater is just part of the movement of water between number 4 and number 6. The way that we determine groundwater movement, we use a basic law called Darcy's law. Darcy was a French civil engineer in the 1800s who worked on water supply in the Dijon, France. He came up with this equation that allowed us to either calculate the discharge of groundwater, and we've changed that to also allow us to calculate groundwater velocity. So this is the basic form of Darcy's law. Q, the discharge, is equal to the hydraulic conductivity or permeability times the hydraulic gradient, small I, times cross-sectional area. And we'll take a look at these later on. But to determine how quickly groundwater moves, we use this form of Darcy's law. V is the average linear orbital velocity, or the average groundwater velocity. K is the hydraulic conductivity. I is the hydraulic gradient, and N is the porosity. So we use this to figure out how quickly groundwater moves, and from that, we can figure out how quickly chemicals move in the subsurface. So hydraulic conductivity is got a huge range, 13 orders of magnitude, from gravel, which is very permeable, down to different types of rock that virtually don't transmit water at all. And you can see rock that's fractured would be more permeable, and so on. The huge variations in hydraulic conductivity depend on the geology, and that's why it's so important to characterize the geology correctly, because that will affect the groundwater velocity. So we measure hydraulic conductivity K. There are field methods, there are lab methods, there are models, and so on, and they all have their merits and demerits. But it's important to recognize that when you see hydraulic conductivity test results, you know, you need to evaluate how the testing was done, because hydraulic conductivity can vary with sample size. For example, if I were to measure right where my cursor is, you know, that'd be a huge hydraulic conductivity. Water would move a lot, but if I moved over a little bit, you know, it wouldn't move much through this rock. But if I had a big sample and I incorporated that, that would give me a value that's different from just the rock or just the void space. Test orientation is important. A lot of lab tests test the flow vertically, but you can see in this var of clay that the groundwater would flow readily through these permeable zones, but not so readily through the clay. So lateral flow would be a lot greater than vertical flow. Some methods, you're taking samples that are disturbed and they don't reflect this kind of structure. So there are all sorts of reasons why you need to look at how hydraulic conductivity testing was done. Hydraulic conductivity has heterogeneity and anisotropy. And the anisotropy talks about, down here we can see that it talks about changes in hydraulic conductivity with direction, and heterogeneity talks about changes with location. So if we look at this sample, the yellow arrow is a clay soil, which will have a low hydraulic conductivity. The white is a gravel, which will have high hydraulic conductivity, will transmit water. So these two areas are different. So the hydraulic conductivity varies with location. So that means that it's heterogeneous. And then the one on the bottom, the photo on the bottom, we're seeing where if we measured vertically versus horizontally, we'd have different hydraulic conductivities. That would be anisotropic soil, because the hydraulic conductivity depends on the direction you're measuring. Hydraulic gradient in Darcy's law is the driving force for the groundwater flow, and it refers basically to the slope of the water table or some other unit that you're looking at. And in the field, we use monitoring wells, and we can see monitoring wells in these two arrows. These other things are posts to protect the monitoring wells. And in the field, we measure the water level, and we call that the head. And that's how we determine hydraulic gradient. So parts of a monitoring well that you don't see in the subsurface, there's all sorts of pieces related to the well itself. There's a screen, which allows water to move in, but keeps soil out. And this is a demonstration screen, so it's got different size openings. The riser is just a plastic pipe or other type of material that allows you access to the screen, to the surface. And then we have some protective casings on top. And then we also have other features in the annulus, which we call that space in the borehole that we put the well into, that we fill up. Things like a sand pack, seals to prevent surface water from entering, so that the screen will just sample groundwater. So if you were to measure water level, you would just open this up and see where the water level is in the well. A lot of wells that you may see in the field are in parking lots, so we can't have pieces sticking up. So we have these things called flush mounted wells. And you'll often see these in parking lots or on gas stations and so on, where the well is below a metal cover. And this is how we measure the water level, so we can get hydraulic gradient. we use what's called an electric contact gauge, and that is basically got a probe on it, and it's also a measuring tape, and you determine how far down you have to go before the probe hits water. When it hits water, you get a buzz, or you get a deflection or a electrical signal. A light will go on, and you can figure out the depth of water. And if you survey the top of the well, you'll know what the elevation of the water level is. So we do that in a number of wells, and then we plot those on a map. So this is how we determine groundwater flow direction and hydraulic gradient. So we ensure that all the wells are appropriate. In this example, all these symbols are wells. And what I mean by appropriate is that the wells are of the same depth and in the same formation. And often people make mistakes, or sometimes people make mistakes and include wells that are in different formations and different depths. So we plot the groundwater elevations on the map and contour the data, join points of equal elevation. And these are the contours here, 102, 101.5, and so on. And then groundwater flows from the high elevations to the low elevations in terms of the groundwater contours. And the contours are drawn perpendicular. So when we look at this line, that's not really a great example, but these lines should be perpendicular, the arrow and the contours. This one's a little better up here. And then I is calculated from the contour map. And basically we take the difference between the values of two contours and divide that by the distance between these locations perpendicular to the contours. And that would give you your hydraulic gradient that you can use in Darcy's law. So we have groundwater flow direction and hydraulic gradient. So the water table is a subdued replica of the surface topography. That means where the groundwater, where the topography is high, the groundwater is high, and where it's low, the groundwater is low. So we can use a vertical, determine a vertical hydraulic gradient, also using a series of wells where the well screens are at different depths. So here we've got one well with the screen at that depth, another one at that depth, and we call this a well nest. So if in the well nest, the deeper well has the lower water level, that's considered a downward vertical hydraulic gradient, where you've got a situation where the deep well has the highest water level. That's called an upward vertical hydraulic gradient. And if you don't see a difference, that means there's not a vertical hydraulic gradient. So if we go back to our topographic picture, we can have vertical hydraulic gradients that are natural or induced. And in terms of natural conditions, generally we find that in low areas, the hydraulic gradient is upward. So generally near streams and lakes, and in high areas like hilltops and so on, you generally have downward vertical hydraulic gradient. So just looking at porosity in Darcy's law, pores are openings in soil or rock. Porosity N is the symbol we use, or the volume of voids over the total volume. So if we looked at this glass, that would be the total volume, and the void space would be between the golf balls. Porosity is expressed as a percent or decimal fraction. It could be primary or secondary porosity. Primary means that it's created when the rock or soil is created. Secondary means it's created afterwards, like we see in this bottom slide where the rock is fractured. We commonly use tables to assign porosity. Rarely do we see people actually measure porosity in practical groundwater problems. So these are some tables from the textbook by Freezing Cherry on porosity with ranges for different grain sizes of soil and different types of rock. And you see fractured rock is potentially has a lot of porosity, and massive rock doesn't. Karst limestone just means it's like caves. But the thing to notice is porosity, the variation is much smaller than what we saw in hydraulic conductivity. Interconnected porosity is what we're interested in. That's the symbol N sub E. And for granular soils like the gravel that we see in here, there's not much difference between the total porosity and interconnected porosity. There is a large difference for clay soils, as you can see in this table comparing porosities and effective porosities. So most groundwater moves very slowly. Darcy's law, velocity is equal to hydraulic conductivity times hydraulic gradient divided by porosity. And I've just worked on two examples with kind of typical values. So typical hydraulic conductivity for a sandy soil would be 0.001 centimeters per second. Hydraulic gradient in a flat topography might be 0.008, and a porosity might be 0.3. That would give us a velocity of 28 feet per year. That's the velocity of the groundwater. For a clay soil, where the hydraulic conductivity is much lower, you can see we've used a typical clay soil effective porosity. The groundwater moves 0.06 feet per year. That's very small amount. So geology, which affects the hydraulic conductivity, will affect how quickly groundwater will move in the subsurface. So some miscellaneous definitions. One of the things that we often talk about are hydrostratigraphic units. These are geologic units or layers with similar hydraulic characteristics or similar abilities to move water. So an aquifer would be something like the gravel we talked about. It's saturated, permeable geologic unit where the groundwater moves relatively quickly for groundwater. And things that are aquifers are like sand or gravel, so fractured rock, or some types of sedimentary rock might be aquifers. An aquitard is a saturated permeable geologic unit through which groundwater moves slowly. Things like clay soils, like we see in the white arrow, shale, which is the type of rock that is clayey, also would be an aquitard. So commonly aquitard, there's other types of hydrostratigraphic units, but these are the two most important ones. And aquifers can be different varieties, and this will affect the likelihood that an aquifer might be contaminated, for example. An unconfined or water table aquifer is one where the upper surface of the aquifer is open to the atmosphere. So this would be like sandy soil all the way to the surface. There'd be no clay soil above it, for example. A confined aquifer is one where the aquifer is overlain by an aquitard, basically protected by the aquitard, and the water levels usually above the top of the confined aquifer. And these are very important distinctions when it comes to things like pumping water out of a well how these behave. They behave quite differently. And a perched aquifer is a situation where you might have a low permeability layer above the water table that would cause a perching of a saturated zone. This may be transient, and you would find unsaturated soil below it. So getting back to our example, which we talked about at the beginning, the former Schilling Air Force Base in Salina, Kansas. It was an active military base in the 40s, 50s, 60s. And it's now an industrial center and an airport, and people live around it, people work around it. And what we wanted to know was, where are the chemicals now? In the 1960s, they were using hundreds of drums of TCE per month. Where did that go? What directions of the chemicals are moving? We know that the city wells are to the northeast of this location. How fast are the chemicals moving, and how do you clean it up? So in order to do that, we looked at the site and we put in hundreds of borings and monitoring wells to establish the geology and the groundwater conditions, see where the permeable zones are, where the zones that aren't permeable are, and which direction were the groundwater flowing, how fast was it flowing. So we were also, with this data, able to put our arms around both the sources, we knew where the sources were, and the plumes of groundwater, impacted groundwater that left the sources. We measured hydraulic conductivity in many locations, and we created groundwater flow maps over a period of 5 years. So we know how fast the groundwater is moving, and we know in what direction it's moving because we've got all the groundwater heads measured and mapped out. So the next step was to develop a conceptual site model, which we talked about in one of our earlier sessions. And that looks something like this on lower right-hand corner, where we generalize the geology so that we can come up with methods that will be effective and cost-effective in cleaning up the contamination that started in the 40s and 50s and 60s. So thank you for watching Geology and Groundwater Basics. Our next installment will be Basics of Chemical Behavior in Groundwater, and I will be doing that session. And in that, we'll discuss how releases of chemicals become groundwater plumes.